Hello students, welcome to week 9. So in this week we will start solving the plane wave interactions with dielectric boundaries. But before we dive into that, I thought I'd show you some experiments with polarizers. We already saw an inspiring experiment with these polarizers and that glass slide, if you can remember. So, I would like to say a few words regarding what these objects called polarizers are, what do they do, and how we are able to use it, right, in order to study wave polarization. Okay. So, a polarizer right is essentially a filter. Okay. Uh, if light of arbitrary polarization were incident on this, it could be a piece of film or it could be a piece of glass like material. So, some sheet, right. So, this polarizer essentially, regardless of what the incoming polarization is, it only sends out polarization of a very specific type. Okay, that is the function of a polarizer. So, each polarizer uh, is often demarcated with a certain axis. Okay, and the axis or direction is to tell what is the axis along which the electric field is allowed to oscillate and send through the polarizer. Okay. So, a linear polarization where the electric field is oscillating in the same direction as the axis of the polarizer experiences minimum attenuation or minimum loss through this polarizer. And for any other orientation for the electric field, there is some partial attenuation and there is complete attenuation of light when it is orthogonal or perpendicular to the axis of the polarizer. Okay. So, we will see this action in a very small video demo that I created in my office. So, let us first look at the video. Okay. So, in that video we essentially have a picture of a smiley face stuck to the wall. Okay. So, there is light from the room lighting that is scattering off of the image and is trying to land into the camera, right. So, let me try to draw the setup. So, there is the image on the wall. I have my first polarizer, right, whose axis is say lined upwards, right, as shown by this arrow, right. So, in the video first I insert this polarizer and what we saw was the image got slightly dim, right, and then we have a second polarizer that I bring in, right. It is also given another name called the analyzer, right. And then you have my mobile camera, right. Okay. So, this is what is happening in the video. So, at the very first scene, you basically did not have any of the polarizers, and then I insert polarizer 1, right. We saw that the image got slightly dim, and then I inserted a second polarizer, the image got further dim, but still I could see the smiley face. This happens when the axes of the two polarizer plates are in the same direction. Okay. So, the polarizer and the analyzer, if they have their axes orienting in the same direction, light does go through, but it seems to be slightly dimmed, right. We will see why this dimming happens. But interestingly, if I toggle the axis of the analyzer or the second polarizer to 90 degrees, right, of the original direction, I saw that the image was completely blacked out, right. So, basically there was no transmission from the image to the camera, right. So, let us try to understand what is going on in this image, in this video. So, when there is some kind of artificial lighting in the room, this scatters off from the image and it is trying to land into the camera, right. That is how we are able to see objects around us. And the light that comes from several of the natural sources, whether it is the sun, candle flame, or even your LED lighting at home, we call them unpolarized sources, right. So, the meaning of unpolarized source is that it is a collection of polarizations in random orientations, right. So, if I were to look at the plane, constant planes of phase, right. For a plane wave, we said that if this was the k vector, I had my E and k, right. And if the electric field vector was aligned to any one particular axis, we said that it was a linear polarization, right. Or if the electric field vector made a contour of circles or ellipses, then we gave appropriate names as circular or elliptical polarizations, right. So, these are specifically defined polarizations for plane waves, right. Whereas, an unpolarized source you can think of is actually a collection of many such plane waves where the orientations of electric field between individual plane waves are totally arbitrary, right. So, if I were to look at these planes of constant phase, I will actually notice that I have electric fields oscillating at all angles, right. I have only shown a select few here, but an unpolarized source is one where we have electric fields oscillating at any point on a plane perpendicular to the direction of propagation in all sorts of random directions, right, and that there is no particular direction that is favored, right. So, this is what we call an unpolarized source. This mainly occurs because the events within your LED light bulb or sun or the candle flame, the individual events of emission of light are completely uncorrelated, right. So, this is why we basically have a collection of different polarizations all jumbled up, and we end up having an unpolarized source, right. So, the light that is coming, that is reflecting off of the image on the wall, is an unpolarized electromagnetic wave, right. So, I can sort of redraw that in this way, right, demarcating that the electric field oscillations are in random orientations, right, and in time. But the job of a polarizer is to ensure that whatever is exiting, right, that the electric field has only oscillation in one particular direction, right. So, that is why I called it a filter, right. So, it is able to filter off a source, an electromagnetic wave, which has electric fields oscillating in different orientations, and it is only able to give you a pure direction, right, very specific direction for the electric field oscillations that is exiting the polarizer. Okay. And the transmission of light through a polarizer, we can think of it in terms of our Poynting vector or intensity of light, right. This is power per unit area of the light that is going through the polarizer. So, the I that is after the polarizer is the I input by 2, right. So, we will not go into the details of how we arrive at this, right, but because there is no preferential direction of electric field oscillation, all directions are equally likely, right, for an unpolarized source. This polarizer only filters out and sends through electric fields that are oscillating in the same direction as the axis of the polarizer, right, and when it does so, it actually filters out some of the light and precisely seems to be half the light, right, which is why we saw that when the first polarizer plate was inserted, the image dimmed down, right. So, now when the second polarizer is kept, right, and when the axis of the two polarizers are oriented the same way, right, we notice that the electromagnetic wave is actually able to make it through both the plates, and we are able to see the image of the smiley face. However, when you rotate, right, this by 90 degrees and you ensure that the optical axes for the polarizer 1 and 2 are perpendicular to each other, we basically block out, right. So, remember the polarizer 2 is only allowing horizontal polarization through, right, but polarizer 1 is allowing vertical polarization through, right. So, since there is a conflict in the directions here, we notice that the combination of polarizer 1 and 2 with their optical axis oriented perpendicular to each other is completely able to block the light coming from the object, right, into the camera. So, this is what we observed. Okay. So, I can also tell you that the I output of a polarizer is I input cos square theta, right. There is also a name for this, it is called the Malus law. Right. So, that there is a cosine square dependence to the output intensity. So, if I were to send in this is the axis of my polarizer, and I am sending in a linear polarization that is tilted at an angle theta from the axis of the polarizer, right. I can say that the output is, if this is I naught, the output is I naught cosine squared theta, right. So, the intensity that comes at the output of the polarizer is essentially cosine square theta, where theta is the angle between the linear polarization of the input to the optical axis, right. So, you can see that when theta becomes 90 degrees, cosine square theta becomes 0, which is a complete cancellation, right. So, when the polarization of the incoming wave, right, the axis of polarization of the incoming linear polarization is perpendicular to the axis of the polarizer, we notice that the polarizer blocks all the light, right. So, this is the speciality of the polarizer. We will not go into the depths of what the polarizer is made of, how is it that it is able to do this, right. But nonetheless, I think as an instructor who has been giving you examples in optics to try and explain the idea of wave polarization, I have been giving you examples of and we will see many more examples using the polarizer. I think it is at least important to know the cursory behavior of a polarizer in the context of a few different experiments. Okay. And we very often as scientists use these polarizers in our experiments to actually condition the source as well as to analyze what polarizations and if there has been an alteration or a change in the state of polarization. Okay. So, for example, if we started with an unpolarized source, but for the experiment I would like a linear polarization, I could use a polarizer to essentially generate or create a linear polarization out of it. And if this linear polarization were to interact with some medium, as we will see, right, even a dielectric boundary or a conducting boundary can alter or change this polarization, and if I wanted to study how much or how has it changed, I can use a second polarizer, right, and understanding just with the intensity of light that is coming through these polarizer plates, I am actually able to make comments on what has happened to the polarization of the incoming electromagnetic wave, right. So, this is a very, very important and very common tool used to condition your electromagnetic waves. Okay.